Is there somebody there? Can you hear me? Hello?
Professor Ben-Artzi? Yes, we are there. We can hear you and we can see your demonstration well.
So everything is in place, right?
Wait a minute, please.
I mean everything is ready. I just wanted to make sure.
Yeah, we're all ready.
Very good.
All good. All good.
Thank you very much. We start in 6 minutes, right?
Yeah, right here.
Yes. Thank you very much.
Ben-Artzi, do you hear us?
Yes, I can hear you very clearly.
I see. This is Andrei Muravnik from the organizers. Your chairperson today is Professor Graziana Crasta from La Sapienza University, Rome. About 3 minutes later, I shall provide him the microphone, and he will start the session.
Very good. Yes, very nice. Thank you. It is very nicely done. You're doing a very good job.
We are very pleased. We are pleased very much that you are ready to participate.
Yeah, with great pleasure. Yes.
So, welcome everyone to this Saturday morning session of the conference. The first speaker of today is Matanya Ben-Artzi from the Hebrew University of Jerusalem, and he will speak about the title of his conference is From Crystal Optics to Dirac Operators, a Spectral Theory of First-Order Systems. Please, Professor Ben-Artzi, you have 45 minutes for your presentation.
Thank you very much. I hope you hear me well. Everything okay? Yes? Do you hear me okay? And
Yes, we can hear you.
Yes. Okay. So please let me know if something is not good. And
You can talk without problems.
yes, very good. Thank you. And so I want to thank the organizers of this conference for organizing a very nice mathematical event. I enjoyed it very much. So thanks everybody. And it's a pleasure to be here with all of you. So my topic is, as was said, crystal optics to Dirac operators. It is a joint work, everything with Professor Tomio Umeda from Japan. So I remind you what are first order systems. You take the operator L is a first order operator. The coefficients are Hermitian matrices, K by K, and it is in Rn. N will be normally bigger than or equal to 2. So we don't deal with the one-dimensional case here. And L is symmetric, formally symmetric on test functions. So this is our operator to deal with. As examples, all of classical physics almost. Acoustic, electromagnetic, elastic waves, inhomogeneous anisotropic media are all in the same category. The Dirac equation of relativistic quantum electrodynamics is also there. And what is important, you look even at the classical treatise of Courant and Hilbert, which is now about 100 years old. And they emphasize that we should study the common features of these systems, all of them together, and to see what we can say about all of them together. So this is the purpose of this talk. I begin by reminding you of the Maxwell operator. It is a 6 by 6 operator acting on the combined vector of the unknowns E and B. E is the electric field, B is the magnetic, and there are two vector valued functions in R3. So in the vacuum, the operator, the Maxwell operator, as you see it, it is a 6 by 6. By O3, I simply mean the zero. It's the 3 by 3 zero matrix. And then it's the curl. As is well known, this leads to the famous Maxwell equations. Dirac operator is again of the same form. HM, I call it. It's alpha dot D plus M beta. M is the mass of a particle. So it is either 0 or bigger than 0. D is as usual D1, D2, and D3. We are looking at it in R3. And alpha is alpha 1, alpha 2, alpha 3. It is the triplet of 4 by 4 Dirac matrices. And every Dirac matrix is given by alpha j, which is the skew symmetric 0, sigma j, 0. And the sigma j's are the Pauli matrices. So if you put all of this together, you get also an operator of the same type. So the idea is to treat, say, Maxwell and Dirac in the same framework. What is the problem? Sorry. The operators that we are treating now are not elliptic. These are first order operators. The spectrum is over the whole line, so they are not elliptic. And we want to apply what I call Schrödinger methods. That is, methods that are suitable for elliptic operators of second order, but it is not second order, it is first order. All of the treatments, normally up to now, were treating Dirac operator by using the basic property that the square of the Dirac operator is the Schrödinger operator. Hm squared is equal to minus Laplacian plus m squared, tensor I4. That is, it is just the scalar operator. And this is a famous property. This is why Dirac actually introduced this particular form of his operator. The domain of Hm is H1, the classical Sobolev space. But it is important to notice that Hm squared is minus Laplacian plus m squared. But Hm is not the square root of this operator, because the square root is a positive operator, more negative, and Hm has spectrum positive and negative. So it is not a square root. And people who work in this field have to go around it. By the way, the minus Laplacian plus m squared square root is the Klein-Gordon operator, or it is sometimes called the relativistic Schrödinger operator. I'll come back to it later. How about the Dirac operator? I start with some very simple facts about these particular operators. So Dirac operator, this is Dirac operator in vacuum without potential, as you said. So it has a symbol HMC. Xi in R3 is the Fourier variable. So HMF, the Fourier transform, is given by the symbol HMC, F hat, for at least for every F, which is a test function in C0 infinity. And HM4, HMC, is a 4x4 Hermitian matrix. It is given by the symbol alpha dot Xi plus M beta. The eigenvalues of HMC are as you see. This is why it is not a positive, not a non-negative operator. The eigenvalues are exactly lambda plus minus, which are the plus minus square roots of C squared plus M squared. They both have double multiplicity, except at the singularity case. So for NXC, since HMC, of course, is Hermitian matrix for every individual Xi. So for every individual Xi, there exists a unitary matrix, UMC, which diagonalizes the 4x4 matrix. So this diagonalization is given by lambda plus Xi, I2, because so in every corner we have actually a 2x2 matrix because of the multiplicity of the eigenvalue. So lambda plus and lambda minus. And if I take now for all Xi, so I diagonalize at every value of Xi, I diagonalize the operator, the function, with the UMC. What I get is a unitary operator G from L to X to L to Xi, which is given by the individual, by you take for every Xi, you take the individual map by UMC, diagonalization. And this is called the Foldy-Wuthuizen-Tani transformation. It is a classical paper from 1950 that had to do with the spin 1/2 particles, first discovery of spin 1/2 particles. And this particular paper has thousands and thousands and thousands of quotations. It's a very active field in theoretical physics. So G is this transformation. And of course, we can get into details. Here is the expression for UMC, one possible expression for UMC as the exponential of a suitable matrix, and where theta m is just the arctangent. If you are interested, in some cases, some very individual, very detailed study is needed, and then you can get details in a nice paper by Balslev and Elfer. They first took it into the mathematical literature from now 30 years ago. Okay, but we will not deal with the exact technical details from this case. Here is the Maxwell operator. So the Maxwell operator, you have a matrix symbol, which is again given by this 3x3 zero matrix in the corners, and then the skew symmetric minus gamma xi, where gamma xi is actually the symbol for the curl in R3. So gamma xi is given, as you see, again by the skew symmetric matrix inside, classical expression. And this will be the operator, so this is the symbol, Fourier symbol for the Maxwell operator. The eigenvalues of the Maxwell operator are now lambda plus, which is absolute value of Xi, and it has a kernel, I'll talk about it, and lambda minus, which is a minus absolute value of Xi. Multiplicity of each of them is 2, and since gamma Xi multiplied by Xi This is just a matrix product on a vector. The kernel of L Maxwell is two-dimensional with basis vectors. So for every Xi, you take, so for every Xi it's a matrix, and it has two null vectors given by Xi in the lower three coordinates and Xi in the upper three coordinates, and the kernel is two-dimensional. If you take any vector function, the Maxwell equations are supposed to give initial data, and for the initial data to find the dynamics of the electromagnetic field. So if you take this initial data vector function with values in C6, and the Fourier transform is orthogonal, so take the Fourier transform of this vector, and it's orthogonal to the kernel for all Xi. Then in particular, what you have is that by orthogonality, that the Fourier transform of the E0 of the electric field is orthogonal to Xi. Xi is actually, as you know, the direction of propagation. And so this is the expression to say in the physical language that the magnetic and electric fields are orthogonal, transversal to the propagation direction, actually. And the propagation of the initial data by the time-dependent Maxwell system yields the solution, EXT and BXT. Both EXT and BXT are superpositions of plane waves, each of which is transverse, in fact orthogonal, to the propagation directions Xi or minus Xi. And of course, if you just take this, so this is a limitation on your initial data. And this limitation is preserved in time. And it was known to physicists. And actually, the terminology used for such waves is TE modes or TM modes. This was introduced by Lord Rayleigh more than 100 years ago. So we are about to study this kind of operators. And now I go to the Dirac, I go back to the Dirac operator, and I look at the spectral family of HM. So EM lambda is the spectral family. I take, for simplicity, F as a test function, and I take lambda bigger than M. That is, the Dirac operator, as you all know, has a gap between minus M and M. And then I take the positive energies. The negative energies are called sometimes the Dirac C. They are supposed to be full. All the places are full by positrons. Okay, so I take now lambda bigger than M, and I look at the spectral family. This is just the L2 square scalar product. So it gives me just the characteristic function of the X's of lambda plus Xi up to lambda, and of course all of I2 because I'm on the positive side. And this is the Foldy-Woothuysen-Tani transformation, as we discussed. Okay, so this is an expression for the spectral family. Simple enough. And I want, for some reason, now to differentiate this spectral family. So the DD lambda, since F is a nice function, I can differentiate. Actually, it is done by the co-area formula. That is when you differentiate a volume integral with boundary that depends on lambda. This is what you are getting. Again, G is the same transformation. And 1 is the two vector consisting of the first two components of GF, of this transformation. Remember, it has 4. We are talking about 4 components. So you take the upper components, the upper 2, because we are looking at lambda bigger than M for this reason. So this is the expression. You see, this expression is valid for M equal to 0, which is called the massless Dirac operator, or the massive with M bigger than 0, which is the massive with mass Dirac operator. So both of them are included. Now I remind you that I'm using the symbolism L2S is the weighted L2 space, namely the L2 space in Rn with weight, which is X, basically Japanese absolute value to the S, to the power S. And HS is the Fourier transform of L2S, which is the Sobolev space in terms of the C coordinates, Sobolev space of index S in the Fourier transform. There is a trace lemma which is related to the fractional Hardy inequality in some sense, and it says the following. Take f hat, so now we are on the Fourier side. Take f hat in HS, take for simplicity n bigger than or equal to 3, the dimension, and S, the weight is between 1/2 and 3/2. Then for any r bigger than 0, the trace operator, the integral, is controlled by a constant, universal constant C that depends only on S and N, but not on R. We are talking about a sphere of radius R, times the minimum between R to the power S minus F and 1, and times F at the HS norm. So if you just remember the trace lemma says that if you have a Sobolev space with index bigger than a half, S bigger than F, then it has a trace on every part of a smooth submanifold. But here you see what is surprising is, first of all, that you can provide an estimate. The estimate is independent of, I mean, it is bounded up to all R, up to infinity, which is not clear. That is the trace operator, all the trace operators for all R's are uniformly bounded. And furthermore, what is also more important in some sense is that as R goes to 0, that is when you are looking at the traces for smaller and smaller spheres, actually this trace goes to 0. So these are important facts about traces in general. I remind you what we did for the massive Dirac operator. So I take now M bigger than 0 for simplicity. And here we have the spectral family. We have the derivative of the spectral family. This is what we had before. So we have this expression. And now we can apply the trace lemma to all this. And we get, applying the trace lemma, we get now that since, by the trace lemma, since we can estimate the HS norm, we have that the d lambda em lambda ff, you regard it now as a bilinear form. And as a bilinear form on HS squared by the HS cross HS. So by a classical simple lemma on representation of bilinear continuous forms, it gives rise to an operator from HS to H minus S, but you go back to the original coordinates. So here you have F hat, but here I want F. So F will be in L2S and L2 minus S with the duality. And therefore, the derivative of EM lambda, FF, gives rise to an operator, AM lambda, formally the weak derivative, if you want, of the spectral family, which is uniformly bounded by this expression using the trace lemma. It is uniformly bounded and uniformly Elder continuous in the uniform operator topology of L2S to L2 minus S. So this gives some functional explanation to the derivative of the spectral family, which has a name. I will tell you later more about it. Now for the Dirac operator, I jump immediately to the limiting absorption. That is, the philosophy is that I'm, of course, jumping a few steps. I'm using this fact, the AM lambda, the fact that I have a derivative, weak derivative for the spectral family, in order, in this study, to get a limiting absorption principle, which first I want to remind you in great detail. So you take the resultant operator of HM, the Dirac operator, and you take non-real values Z, so it exists, it's a self-adjoint operator, and then you look at the limits as epsilon goes to 0 from above, from the upper half plane or the lower half plane into the spectrum. And the spectrum, I remind you, is everything outside of the gap between minus M and N. I take M bigger than 0 for simplicity. So these limits exist in the uniform operator topology of B L2S L2 minus L for any SL bigger than 1/2. If SL are both bigger than 1, then the limits exist for all mu in R. That is, they are continuous across the thresholds at mu equal to plus or minus n, where you have a threshold that is the point of the boundary point between the spectrum and the resolvent set. So this is the kind of result, that is that the limits exist in this particular operator topology. Furthermore, in both cases, the limit functions are locally bounded and locally held continuous in their respective domains with the topologies with respect to the uniform operator topology, but the uniform operator topology of this L2S into L2 minus L. S and L both bigger than 1 half. Now, in general, the limiting absorption principle is one of the miracles of PDE theory. This means that for all the relevant, say, differential operators from mathematical physics, the behavior on the spectrum is not arbitrary. It has some very nice discipline that you can actually look at the kernel. In some sense, if you want, this is the functional analysis counterpart to the pseudo-differential operator, or to, if you want, the singular Calderon-Zygmunt theory. That is that the resolvent on the spectrum can be obtained by some kind of a convolution with the singular kernel, right? So the singular kernel is exactly what is given here in more detail, because the pseudo-differential theory does not deal with weighted L2 spaces normally. So this is like dividing by the symbol, if you want, this particular principle. And the background, so the limiting absorption principle for the massless Dirac, the first treatment is quite recent, actually, by Kari, Gastesi, Kad, Levitina, Nichols, Potapov, and Sukhochev, and they gave the limiting absorption principle for massless Dirac operator. This is a paper from 4 years ago. And in the massive Dirac, when m is bigger than 0, there were all kinds of attempts and partial results, as you see by Yamada in Japan in 73, then Jensen Kato, a famous paper, and Balslev Helfer in 1992. But we give here a much more detailed and precise form. Now, before going on with the limiting absorption and the relevance to the study, I want to give a very quick reminder of a general form, a general framework to the limiting absorption principle. How you can actually obtain the general limiting absorption principle by using facts like trace estimates and so on. And this has been a long work for many years with Alan Levinatz from Chicago. And maybe a quotation is that I had a survey called the Smooth Spectral Calculus now in 2010 in this volume, edited by Demut, Schulze, and Witt, and appeared in Springer, partial differential equations and spectral theory. Yeah, there are other abstract approaches. There is the classical, of course, by commutators, approach by Moore, the Moore estimates from 1981. This is very well known. And more recently, energy estimates by Girard in France, in Paris, from 2008. So there are abstract approaches. And the abstract approach that I tell you here is the following. So we go to a completely abstract framework, nothing to do with any differential operators to begin with. And the structure is this: you take H to be a self-adjoint operator in Hilbert space, script H, and RZ is the resolvent as usual. E lambda is the spectral family, and you assume that you have a space X, normally a Banach space or can be a Hilbert space, which is embedded in H, in the space H, continuous dense embedding. Now, this is a general abstract fact, but you can think of L2S with the with a positive S, a weighted L2 with some positive weight in L2, right? So it gives you functions that have some kind of growth at infinity, and so it is a stronger norm. So it is a stronger norm and therefore continuously embedded in H. And then by the standard identification of the dual H becomes, via the scalar product, becomes part of the dual of X. So X star is bigger than H, of course. Or this is standard setting. Definition. You say that H satisfies the limiting absorption principle at a point lambda in R, any real point, if, again, the limits R lambda plus I epsilon, where the approach to the spectrum or to lambda on the real axis is from above or from below, from the upper half plane or the lower half plane, if these limits R plus minus lambda exist in the operator topology, uniform operator topology of X star, which we assume are part of the structure. So this is what we call the general abstract limiting absorption principle. So limiting absorption principle means that we want on the spectrum or at any point in R, not even the spectrum is important, but any point in R, to have limits of the resolvents. Of course, the limit blows up if you are in the L2 theory, if you are just in H. It makes no sense because this is exactly what the spectrum is. Definition. Now a definition, take any open set in R and an index alpha bigger than 0 and less than or equal to 1. We say that H is of type X star alpha U if there exists an A lambda, an operator, bounded operator from X to X star, such that, you see, the derivative of E lambda xy, so this is the scalar product in H, but you take it only for xy in the smaller space X. So if this derivative is A lambda xy, this is the duality between X star and X. So A lambda X is in X star. A lambda is from X to X star. And A lambda minus A mu in the uniform operator topology is locally Helder continuous with lambda mu in any compactly contained K in U. So this is what we call an operator of type X star alpha U. Theorem. If H is of type XX star alpha U, as above, then it satisfies the limiting absorption principle in U. It has exactly the limiting values. And the proof is one line in some formal sense, because you use the Privalov-Kohn standard theorem in harmonic analysis. If you want, it's the conjugate function of a Helder continuous function. That's the harmonic analysis equivalent. You write the resolvent as dE lambda over lambda minus Z. dE lambda formally is A lambda D lambda, because this is what you assume. And now you're exactly in the situation of a conjugate function. And by the Privalov-Kohn theorem, you know that the limits exist exactly in C alpha. So, okay, so this takes one concept and makes the limiting absorption principle as a result. The point here, and I'm not going to discuss it very much, because the point here that this is very easy to verify. The fact that an operator is of this type with X, say, in weighted L2S space, this is something that you can verify exactly as we did for the Dirac operator. This is the connecting point. Remarks. A lambda, so A lambda is, again, let me remind you, this is the derivative of the weak derivative, if you want, with respect to X star of the spectral family, T lambda. By the physicists, if you take any quantum mechanics book, this is called the density of states operator, which means that you are not expecting an eigenvalue. If it is lambda is an eigenvalue, A lambda will be infinite. It blows up. But if A lambda is simply big, this means that many states are near that point lambda. It is an almost eigenvalue. So density of states is the name for it. And now a more technical remark. If H satisfies the limiting absorption principle, it does not mean that f of H satisfies limiting absorption principle, even if fH is H squared. So this was a very big obstacle sometimes to all kinds of discussions. You have H, you want to take any function of H, say the spectral family or the square or anything, but this, you cannot have a theorem saying that if H satisfies, then also fH. But if H is of type X star alpha U, this means that you have a full calculus. This is why I called it a smooth calculus. fH is also of type X star alpha FU for a big family of functions f. Say if f is uniformly Lipschitz, for example. The abstract framework can be extended to H plus V, where V is short range in a suitable sense. And so, you see, everything is okay?
Yes, everything is
Okay.
okay.
So, sorry, it was my mistake here. I pushed the wrong button. The abstract framework can be extended to H plus V, where V is short range in a suitable sense. But still, there is no good abstract theory for long-range perturbations. So I invite all the experts in the audience, everybody, if you want, this is still a challenge to have an abstract theory for long range, say something that is the scale of Coulomb potential in the Schrödinger operator. To have an abstract theory for that, we don't have. It's only for short range. Okay, this is a general, I thought it was a good idea to put here a general development of the limiting absorption principle as it developed over the years. It started with, I believe, with Eidus in Moscow in the 60s. He was the first, but then Ikebe Kato in Japan and Berkeley. Willy Jaeger contributed from the beginning. I believe he's in this conference now. Kuroda, a student of Kato. Then in the 70s, it was further taken by Agmon, Edmond Gautier, Hermander. There is a famous paper by Agmon and Hermander about that, Mochizuki, Moore, Saito. And then low-order perturbations of constant coefficients elliptic operators. This was what all of this did in the 1970s. Then the n-body case was successfully done by using the Moore estimates by Perry, Siegel, and Simon in the late 70s, beginning 80s. And the L and the limiting absorption for the periodic case in the divergence form was done relatively recently in Japan by Murata and Tsushida. The periodic case, the Hill equation, so-called, was done by Weidmann also in Germany in the 70s. So then physical models were treated a lot. Various physical models that are related to more physical operators. These are with top order variable coefficients. That is, you don't just take a perturbation like a potential, as in the case of Schrödinger, but you take acoustic or elastic propagators in non-uniform media, layered media. So in the 1980s, it was my work with the French group, Elisabeth Kroc, Darmanjan, Guillaume, and then in Japan, then in France, Bertin, Vega, Weather in Mexico. The divergence form with smooth coefficients, and now the divergence form with smooth coefficients, you can simply look at it. This is the semi-classical study. Exactly, semi-classical techniques. If the coefficients are smooth, so these are Melrose, Ralston, Robert, Chestran, away from thresholds, and then it was done by Boni, Bouclet, Hefner, near thresholds in 2008 in the smooth case. So this is the semi-classical treatment near the threshold. And then I did some work on non-smooth coefficients in divergence form that appeared between the years 2008 and 2010. Okay, now what can you do with this once you have the limiting absorption principle? Sorry that I don't have time, so I don't show you how actually the proof is done from the operator, from Dirac operator, using the trace lemma to get the limiting absorption principle for HN. But once you have the limiting absorption, you can take the Dirac operator, the evolution operator in time, and then you look at the full Dirac equation in vacuum that is still with no potential. And then here is a theorem. You take m bigger than 0, so I take the massive Dirac case. I take s bigger than 1, and let uxt be the solution to this system, the Dirac system. There exists a constant depending only on s and m, such that what you get is the global space-time estimates. That is, even though, I want to emphasize, even though the Dirac operator, like the wave equation, is actually a first order, it is not a dispersive equation like the Schrödinger operator, for example. So it's not dispersive, but yet it has this dispersive effect. You see that you can integrate over space and time with a suitable weight, which shows that actually the solution leaves every ball in a time that can be estimated. See, it means that in every ball, if you take a ball x less than b, then this integral will be finite over the ball for infinite time, which means that it decays very fast from every ball in space. So this is weighted. This is a new estimate for the Dirac operator, and it should be compared to Schrödinger operator, where it exists, and it is a lot of work was done. To those of you who know a bit more about this, for this one, there is no equivalent Strichhartz estimate. There is no Strichhartz estimate for the Dirac operator. Let me continue. I'll just jump. I wanted to bring this. I have about, 7 minutes to go?
Yes, almost 7 minutes. Yes.
Okay, very good. So I'll jump this one. And I'll just give you a flavor of general systems. So the title of my talk was that I'm going for all the general systems. So let me try to give some very brief introduction to that. So I go back to the general system where L is mjx dj plus m0x, and now I take with perturbations. So L is, I consider it as a perturbation, what is called the top order perturbation. It's not like I add a potential, but mj0 is perturbed. The top order is a perturbation of L0, and these are constant Hermitian matrices. Non-commuting, that's a very important point. So these are non-commuting. So the addition of M00, it looks trivial. Why should I add this constant matrix where I could absorb it somehow or shift it? But it is not so simple, and it gives a lot of problems. The fact that you need, and we need it if we want to include a massive Dirac operator in this business. So let us look at the time evolution right away. So first we start with the time evolution of the homogeneous operator, the unperturbed operator L0. So you have this equation, and of course you go to Fourier space as usual, and you take the symbol, and the symbol, of course, is what we saw before. It's the homogeneous part which gives rise to a first order polynomial in C, plus the M00. So you have a very explicit symbol. And the solution is very pleasantly given by this formula, kind of simple formula that you go to Fourier space. Point is that if you want to have any description of this evolution operator, which means that you want to have some global in time parametrics, right, for this equation, then you are in big trouble in general because of the non-commutativity And then I remind you this, in order to get this and to have a control on this evolution in time of M tilde, this is what is called the Weil calculus. You take the eigenvalues, I'm not entering into details, you take the eigenvalues and you take the projection Pj is the projection on lambda j. Lambda j is now the eigenvalue number j of M tilde. So you take the finite dimensional spectral decomposition, if you want. All the lambda j's are real numbers, and you get uj. And every uj, every component, is given by the, I now take radial coordinates with respect to lambda. That is lambda and c on gamma j on the surface. And so this is like the co-area formula. So uj is given by this explicit formula, where you see that what happens is that you have the gradient of lambda jc, and this is the source of trouble, because if you have coincidence, for example, then lambda jc has no gradient, and or a gradient that blows up, something like that. So this is the kind of study for the time evolution, and what we propose is a study that goes around all these difficulties. So this is typical if you work in classical theory, pseudo-differential operators, actually Fourier integral operators at this point, but if you want to do it differently, by functional analysis. I mentioned some papers that deal exactly with such behavior of systems by Jeff Rauch, hyperbolic partial differential equations, Wilcox, asymptotic wave functions and energy distributions, weather, analyticity of the, because all these are physical systems, like crystals and so on. And if you want to go very deep into the subject, you have to go into very detailed coefficients. So for the first, if you look at the limiting absorption principle for the background for first order systems, so this is, as I said, this is the miracle, the functional analysis side of the pseudo-differential treatment. Then the first was homogeneous uniformly propagative. I'm going to remind you what are, very briefly, what are uniformly propagative systems. So Tamura in Japan, and then Weather for strongly propagative. And for non-homogeneous systems, it seems that there was no previous work to what we are now discussing. Now, briefly, all the common physical systems, Dirac, Maxwell, wave propagation, elastic medium, and others, share the basic property of being strongly propagative. Here is the definition. You take the homogeneous part of your operator, and you say that it is strongly propagative if the symbol M homogeneous has a kernel of fixed dimension D. It can be 0, but it can be bigger than 0 for all Xi, for every individual value of Xi other than the origin. So please note, this means that we have a Hermitian matrix for every Xi, and the Hermitian matrix has a kernel of dimension D. This kernel changes. It will not be the same kernel for another Xi, but it will have the same dimension. This is the astonishing, if you remember with the Maxwell equation, it was 2. And the 2, of course, was different for every direction, but it was always a kernel 2 that supported the TE and the TM modes. And of course, once you have this, you have the singularity set of eigenvalues. Roughly speaking, instead of looking at the algebraic language, this is where the eigenvalues coincide. And where they coincide, this is a very bad set. So Z is the singularity set of the eigenvalues. And then the negative and positive eigenvalues of M are equally number, positive, homogeneous. And Z, it so happens, the singularity set is a conic set, is a closed cone of Lebesgue measure 0. And every eigenvalue of M homogeneous has constant multiplicity if you go outside of this conic set. And the distinct eigenvalues are real analytic outside of the conic set. So the conic set is big headache. This is the main problem. If you want to go to more restricted classes, where the conic set does not exist, these were the first treatments, then you call it uniformly propagative. In fact, the Maxwell equation, the Maxwell operator is uniformly propagating. It is strongly propagative, and moreover, the eigenspace associated with every eigenvalue has a constant dimension, independent of C. And this includes the eigenvalue 0. Another class of physically relevant non-homogeneous operators is the isotropic operators. And then what is called the slowness surfaces are spheres in this case because they depend only on the absolute value of C. And then you have the limiting absorption principle for homogeneous, strongly propagative operators. This is back to our work now that I'm reporting. So you take any lambda j c and you take C away from the singularity. It's a non-zero eigenvalue. And you look at the slowness surfaces of the system. The slowness surfaces are exactly the points where lambda j c is equal to the sign, so that you have positive and you have negative. So you take it, the negative eigenvalues will be -1 and positive. So these are typically manifolds. They are open smooth submanifolds of codimension 1, but they don't touch, the boundaries of such manifolds are exactly the singular set that I'm not excluding. And they are bounded and bounded away from the origin, but they can form a cusp. When they get to the singularity, there is a cusp so that you cannot deal with the gradients of the lambda jx's. In the language of Courant-Hilbert, in the classical language of wave propagation, these slowness surfaces were called normal surfaces. Now, I see that I'm out of time. The next thing is...
You have run out of time.
Yes, I'll just conclude by saying,
1 minute, please.
Yes, I'll just conclude by saying that there is a study, a technical study of how to actually deal with such singularity sets, but I have to stop here. Thank you all, and in particular, special thanks to the organizers of this nice conference. I stop here.
Let's thank our speaker. Are there questions, comments?
The page 27, please.
Page 27.
Page having the spectrum of massive Dirac operator. This is far away.
Yeah.
That's a jump.
I'll go to the spectrum of the... yes, 27 in this counting. You mean...
overshoot.
This is?
We were already at the correct quest, but you got some pages.
Yeah.
The spectrum must be a closed set, but the complement to a segment denoted by square brackets is not closed, but open.
Yes. Actually, the spectrum contains, of course, the boundary. You are absolutely right. But for the limiting absorption, we cannot go directly to the threshold. And in fact, we can go to the threshold if SL is bigger than 1, then we can go also, and to have this is remarkable, also to the threshold. But of course, the spectrum contains both points -m and n. But for the limiting absorption, if I want the minimal assumptions, I can go only before the threshold. I cannot go to -mm. This was all the previous works. So you're absolutely right that here we can go also to the threshold. The spectrum is closed. Yes.
There are two cases where mu is from interior of the spectrum and from the boundary points.
Exactly. And if you see, if I want to go to the boundary point and to get some meaningful, and all our theory is including the boundary, this is why we can get the space-time estimates, of course, then we need to make a stricter assumption that SL is bigger than 1. Both SLN, so you see, for the general theorem, which is like the previous theories and some of the previous papers, we take SL classically as bigger than 1/2. This is the classical case for weighted spaces. But if SL is bigger than 1, we can get a more successful principle. And of course, you need it if you want global space-time estimates. Otherwise, you don't get them because you don't know how Rm plus minus, how the limiting values explode as you, exactly as you said, as you approach minus M or M. Exactly.
Okay, thank you.
Are there other questions or comments? Okay, if not, let's thank again our speaker. And we will resume in 3 minutes.
Thank you very much.
Thank you.
Madania?
Yes.
Can you hear me?
Yes, I can hear you, Willy. I can even
I have a question, but he didn't take it. Short and long range. We know this, that it's related with asymptotic behavior at infinity, which is usually I call Cauchy uniqueness problem at infinity. I would like, what is the reason knowledge we cannot discuss now, but you may inform me. I still Schmur had for the elliptic case the short range in for even higher system where it goes like a power of 1/x to 0 to a constant. But I never saw a proof for this. Mostly it's used exponentially decay. And that's a very interesting problem of the Cauchy problem, a uniqueness problem at infinity.
I see. That is because the reason is that the long range means that you don't get the WKB. The WKB leads you, there is a logarithmic shift even for the Coulomb potential, which was known to
potential is this, but this is already very often it's further decay to not. I'm not looking at the Coulomb potential now, but constant variable coefficients. And the decay usually, I asked once Hermann, who gave proofs for exponential decay to constant, but he couldn't go to other decays, and he said it's a very complicated problem, he will not attack it. But what is the state of the art? Maybe you can tell me by email. I would be interested.
Yes, yes. If you know what, really, if you, nice to talk to you, first of all, but if you send me a line to my email, and then I'll be able to see. I don't know your email.
Yes, it's yes. I sent you. I have your email. Then I sent you.
Yes, please
and
send me.
It's great to see you and to hear you again.
Yes, it is. Yes, from time to time we remember how long ago it was. All the meetings in Minnesota and everywhere, but in Heidelberg.
I also remember Jerusalem.
Yes,
but I have to stop the discussion because the report. Yeah.
Okay, go ahead. Go ahead now. See you.
See you. Talk to you later.
Okay, hi.
So I think we can resume with our next speaker, which is Nazaikinskii from the Ishlinsky Institute for Problems in Mechanics of the Russian Academy of Sciences, and he will speak about efficient semi-classical asymptotics. Please.
Yeah, thank you. I hope people can hear me. So today I will speak about efficient semi-classical asymptotics. First of all, I would like to thank the organizers for the opportunity to give a talk here. And the results which will be discussed in this talk are obtained in joint work with Sergei Dobrokhotov and Andrei Shafrir, and also with the staff of our Laboratory of Mechanics of Natural Hazards in our institute. Well, and let me first discuss what I will discuss. Today I will talk about, very briefly speak about Maslow's canonical operator, which is the main tool in semi-classical asymptotics, just a brief reminder. Then I will give new formulas and explain why they are needed. Discuss asymptotics near caustics via special functions, and if time permits, some extensions of the canonical operator, but I'm afraid this is not going to happen owing to time limits. So first, a brief introduction. There are, of course, quite a few people who study semi-classical asymptotics, and it is important to list them also. Here I give only some very basic steps. This is the invention of the WKB approximation by Jeffries, Wenzel, and Kramers. In 1965, Maslow introduced the global tool for constructing semi-classical asymptotics known as the canonical operator. And the notion of Lagrangian manifold was introduced in his 1965 book. Well, and in 1971, Hermander introduced his Fourier integral operators, mainly based on Maslow's ideas, but there was an important new element that is arbitrary or general phase function. And here are some, of course, just a random choice of some people who also deal with semi-classical asymptotics later. The thing is, the canonical operator was invented more than 60 years ago, when there were essentially no powerful computers at the time, and so it was largely a theoretical tool for studying semi-classical asymptotics. But now, with the introduction of technical computation systems such as Wolfram Mathematica or MATLAB, the requirements on mathematical tools become different, and so there is a need to construct really efficient formulas which can be really implemented on such technical computation systems. Well, and that's why the need for the new formulas arose, and so we will discuss them. But first of all, I will introduce the class of equations we consider and the basic information about the canonical operator. So we consider equations of this form. H hat u is 0, for example, where H is a differential, pseudo-differential operator with a small parameter mu, which multiplies the derivative. Some examples include the Schrödinger equation, where mu is H, the Planck constant, and wave equations, also the Helmholtz equation, where mu is the reciprocal frequency. So semi-classical asymptotics mean rapidly oscillating asymptotic solutions of this equation as the parameter tends to 0. The simplest example is given by WKB solutions. These solutions of this form, where S of x is a smooth real valued function. We don't consider complex valued phase functions in this talk. A of x is a smooth amplitude, and S satisfies the Hamilton-Jacobi equation. H of x ds over dx is 0. The equation P equals ds over dx specifies the Lagrangian manifold associated with this WKB solution U. The manifold is Lagrangian. This means that its dimension is n, and the pullback of the symplectic structure on this manifold is 0. WKB solutions are associated with Lagrangian manifolds diffeomorphically projected onto the coordinate x-plane. As we construct solutions, the Lagrangian manifolds move along the trajectories of the Hamiltonian vector fields of the Hamiltonians involved in the problem, and so the condition that they are diffeomorphically projected on the x-plane can be evaluated even if, say, we deal with the Cauchy problem and the initial time this was the case. This might not be the case at some later point in time. And so WKB solutions alone are not sufficient. One needs more complicated solutions, which are provided by the canonical, well, okay, provided by the canonical operator. So let me discuss the classical construction of the canonical operator in the one-dimensional case. Here is the phase plane xp and Lagrangian manifold lambda. If it is projected onto the x-plane as shown in the first picture, then it is given by an equation of this sort, and the canonical operator is just the WKB element written here. Here we also have some Jacobian here, which represents some density defined on lambda, some volume form. Well, okay, if Lagrangian manifold, however, is not diffeomorphically projected on the x-axis, it is projected on the p-axis. Well, and then it is given by an equation of this sort, and we again can write a WKB element, but unfortunately this WKB element depends on the wrong variable. It depends on the variable p, while we need x. So to obtain a function of x, we can rotate the picture by the angle of pi over 2, but in for function space, it corresponds to Fock quantization of this rotation, which is canonical transformation, and this quantization is just the Fourier transform with the parameter mu. So we get this formula for the canonical operator in the so-called momentum representation. In the general case, the Lagrangian manifold is covered by coordinate neighborhoods, each of which is projected either to x or to p diffeomorphically, and these representations are glued together with the help of a partition of unity. Well, in this process, the quantization condition occurs, which permits us to carry out the pasting together for all the charts. But we will not discuss it together. We will not discuss it today. Today I only resort to local theory. This was one-dimensional case. In the many-dimensional case, one has to use partial Fourier transforms with respect to part of the variables in the general case. Well, okay. So what are the disadvantages of this construction? The main disadvantage is that we use unnatural coordinate systems on the Lagrangian manifold. These coordinate systems are, well, okay. These coordinate systems are as shown here, some variables x and some variables y. These are the variables in the coordinate neighborhoods of Lagrangian manifolds. But these variables are not naturally arising in the problem we are being solved, and so we must do unnecessary work. First, we express the functions on the Lagrangian manifold by these parameters, then we integrate, and so this is, in fact, very inefficient. On the other hand, when you solve some problem, then the Lagrangian manifold that arises in your solution usually already has some natural coordinates. For example, if you consider an eigenvalue problem, and in the integrable case, the asymptotic eigenfunctions are associated with Liouville tori. On these tori, you have the angle variables, which are natural coordinates on these Lagrangian manifolds, but they have, in general, nothing to do with this artificial partition into x and y variables. So the need arises to give formulas for the canonical operators, which represent the canonical operators in arbitrary coordinates on the Lagrangian manifolds. So we obtain a Lagrangian manifold, we have some coordinates, natural coordinates on this manifold, and we express canonical operator in these coordinates. This is the first line of work. The second line of work is that in a neighborhood of caustic, the solution is represented by a rapidly oscillating integral, which is also not very easy to compute for small values with the parameter. But if the caustic belongs to some standard list of generic caustics, say in low dimensions, these are fold, cusp, and so on, then you can represent the canonical operator via special functions, thus eliminating the need to use integral. So this is the second line of work, which is to represent the canonical operator in the neighborhood of generic caustics via special functions. And the third line of work is, of course, extension of the canonical operator to wider class of problems, because, say, when you deal with equations of wave type, say, Petrovsky hyperbolic systems, then you end up with Lagrangian manifolds which will have singularities at zero value of momenta. And here the standard canonical operator also doesn't give an answer, and this must be generalized. Also, there are other cases, but I will not speak of them today. So let us proceed to new formulas. First, I recall general oscillating integrals, which essentially these were introduced by Hemander in a different situation of asymptotics with respect to smoothness. And so this goes as follows. A non-degenerate phase function defined on some open set V in the product of Rnx times Rm theta, where theta there are auxiliary variables, is a function such that the differentials of the derivatives of phi with respect to the theta variables are linearly independent of the set C phi defined by this equation. Phi by theta is 0. And then this C phi is a smooth manifold, and the mapping J phi written here, which takes each x theta to x d phi to dx, maps C phi onto a Lagrangian manifold in R2n with coordinates xp. And so if this Lagrangian manifold is some open domain in our Lagrangian manifold lambda, then we obtain a local chart on this larger Lagrangian manifold, and we can represent the canonical operator via the oscillating integral with this function phi of x theta. Here are some details, but they are not essential, so I omit the discussion of these formulas. The important thing is that we can define Lagrangian manifold by non-degenerate phase functions and write the canonical operator as oscillation integral with the same phase function. The original Maslov definitions of canonical operator is a special case of this, very special, where this phi has very special form. But here is the general definition. It is not convenient if we stop here, because we just cannot tell how to conveniently construct this function phi. So I will now give the recipe. Well, consider Lagrangian consider the Lagrangian manifold lambda given by some functions x of alpha and p of alpha. These are local coordinates. Then on these manifolds, we locally have the action function, whose differential is pdx. And let's also define a volume, take a volume form of this Lagrangian manifold. Well, I introduce the universal phase function S of x alpha, which is equal to the action plus this product, p by x small minus x capital of alpha. So how to construct a local canonical operator? Assume that we take some point alpha naught in our Lagrangian manifold such that the rank of the Jacobian matrix dx over the alpha is equal to some number k. Then I can split the coordinates alpha into two groups phi and theta such that the rank of x phi is equal to k, and there are exactly k variables phi. So the matrix x phi, it has this rank, so it has a left inverse phi, and I introduce this equation, which has a solution, a smooth solution. Phi is phi of x theta. Now I can substitute this phi into my universal phase function and obtain a function phi of x theta. This is a generating function of our Lagrangian manifold, a phase function, and so we can use this function to represent the canonical operator according to the general formulas essentially due to Hermanter. Well, the breakthrough here is that we have a very explicit construction of this phase function. We have our Lagrangian manifold, we take some natural coordinates alpha on it, and then we can construct this function in a very direct way. Okay, the simplest, next page, please. Well, the simplest, thank you. The simplest case here is if we have canal coordinates on our manifolds. Let me explain. Assume that locally on lambda we have the differential of action d tau is non-zero. Then there exists n-1 function psi on lambda such that the functions tau and psi are local coordinates on lambda. These coordinates are called acanal coordinates. So we write x is x of tau psi and p is p of tau psi. Assume that the determinant of this matrix is non-zero. This is n by n matrix. Then we can define tau as a function of x and psi from this equation. This is just a special case of the equation I have written on the previous page. Well, and then we can write the canonical operator in this very simple way. This is a very simple formula. Here is just tau. Here is the amplitude. Here we substitute this tau of x and psi, then we integrate. Let me give a simple example of this. So the example concerns Bessel functions of integer index. I recall that they are defined by this equation and have this integral representation. Now, for now, let's pretend that we know nothing about this integral representation and try to compute the asymptotics of G and R as the number tends to infinity and or the argument tends to infinity. Well, let's do so. So consider the space R2 with coordinates x and with polar coordinates R phi. And introduce the function u of x mu equal to e to the power I n phi jn of R over mu. Here we assume that n is gamma over mu, where gamma varies in some bounded domain. Well, consider these two operators. H1 is minus mu squared, the Laplacian operator, and H2 is this operator written here, rotation operator, in fact, infinitesimal rotation. And then H1u is equal to u, and H2u is equal to gamma u. So we have the symbols of these two operators are written here. This is just sum of square, and this is the x1 p2 minus x2 p1. These two Hamiltonians are in involution, and so we can readily obtain a Liouville-Lagrangian manifold, they are common level. It is not compact, but nevertheless. So let us consider this Lagrangian manifold. It is given by these formulas, these xp in R4, so that p square is equal to 1, and this x1 p2 minus x2 p1 is equal to gamma. Or this manifold can be described parametrically by coordinates alpha and psi in the form x is equal to this expression and p is equal to this expression, where n of psi is the unit vector in the direction of psi. Well, so let me show how this manifold looks like. Unfortunately, I can't show the four-dimensional space, so here I show this manifold in the coordinates x2, x1, and the vertical coordinate is the parameter alpha. It is shown here for gamma non-zero. We see that this manifold is diffeomorphic to a cylinder, and one can verify that alpha null, alpha is equal to 0, are the focal points. There's the points where the diffeomorphic projection onto the x-plane is violated. And here I have drawn half of this manifold, only alpha positive, for gamma equal to 0. The coordinates are different, x1, x2 plus pi 1, and p2. So some impression of how this manifold looks like we have here. So this is Lagrangian manifold. Let's construct canonical operator on it. So I once again these formulas for the manifold. The action or A canal can be taken in this form: alpha plus gamma psi, and tau psi are coordinates on this manifold. So these are A canal coordinates. The determinant of this matrix is equal to 1. We can take the invariant measure, the sigma on this manifold, and the equation Px minus x is 0 leads to the following expression for tau of x psi. Tau is equal to the inner product of n of psi by x plus gamma psi. The amplitude in the canonical operator, which is the solution of the transport equation, in fact, two transport equations corresponding to two Hamiltonians, can be taken equal to 1. Here is the general formula reproduced for the canonical operator in the A-canal coordinates, and here is what we obtain when we substitute these solutions here. Well, a very nice formula, and from this formula we readily obtain the exact formula for Jn of R. So in what we see in this example, if we tried to write the standard canonical operator on our Lagrangian manifold, we would have used at least 4 coordinate neighborhoods with different coordinates. We would write 4 expressions and then use partitions of units to glue them together. If we use these A-canal coordinates, we get only one chart, only one coordinate neighborhood. This coordinate system is global here, and moreover, in this example, we obtain not asymptotic, but even an exact formula for the Bessel function. So this shows how these coordinates work in examples. And now I proceed to the second topic, which is representation via special functions in neighborhoods of caustics. Well, okay, so these are some people who studied such representations. And let me start from asymptotics in the neighborhood of a generic fold. Well, consider one-dimensional case. Canonical operator on Lagrangian manifold with a turning point. Here is our Lagrangian manifold. Here is the turning point, x0, p0, and there are two branches of our manifold, so say lambda plus and lambda minus. So if the coordinate on lambda is alpha, so we have two functions, alpha plus minus of x, which specify the upper branch and the lower branch. And also the function alpha is alpha of p, which defines this manifold in the coordinates p. So to define the canonical operator, we need these functions s plus minus. These are obtained by taking the action and substituting alpha plus minus of x for alpha. Also, we need the function s of p, which is given by this formula, and three Jacobians, the x for the alpha, and at the points alpha plus minus of x, and dp for the alpha at the point alpha of p. If we know all that, so let phi of alpha be some function of lambda. So what is the canonical operator applied to this function? Well, first consider the case in which x is greater than x0 plus delta, where delta is some positive number. So x lies to the right of x0 and separated from x0 by some, at least by delta. Then the canonical operator is a sum of two WKB expressions written here. The first expression corresponds to the upper branch, and the second expression corresponds to the lower branch. Well, assume that x minus x0 is less than delta. Then we need to use the momentum representation, and we get this formula. And finally, if x lies to the left of x0 and away from x0, at least by delta, then the canonical operator is O of mu to the power infinity. It is small because the projection, there is no points for Lagrangian manifold over these points x. So these are expressions. Assume, however, that we have a fold that is the Lagrangian singularity of type A2 according to the classification by Arnold, Warchenko, and Gussein-Zadeh. This means that x is, if we represent x as f of p, then the derivative of f at pi naught is 0, and the second derivative is non-zero. Then one can simplify the canonical operator, and namely we can eliminate the integral by expressing it via the area function. So how this is done? Well, consider first the standard fold, x is equal to p squared. Then the canonical operator can be written in this form, where a is related to phi by division by the square root of a Jacobian. If a is equal to 1, then the canonical operator is just the area function times this factor. This is the standard integral. What to do if the a of p is not 1? Then we can represent a of p in this form, f0 of p squared plus p f1 of p squared, where f0 and f1 are smooth functions. And we can write the canonical operator substituting this for a of p. And now notice that we can replace p squared here by x. Indeed, f of x minus f of p squared is x minus p squared times some smooth function g of xp. And this x minus p squared is the derivative of the phase function px minus p cubed over 3. And once we have the derivative here, we can integrate by parts, and we obtain lower order terms. So what we get here, now we can take f0 and f1 outside the integral, because they do not depend on p. This p here gives the derivative. We obtain the following answer, modulo lower order terms. Our canonical operator is represented by the area function and its derivative. Well, this was in the standard case. Well, and assume we have a general A2 fold. Then there is a change of variables which reduces the case to the standard fold. And after this change of variables, we obtain the area function and its derivative of some composite argument. But how to find this change of variables and compute these expressions more easily? There is a simple trick which we'll now show. This trick is based on the asymptotics of the area function as the argument tends to minus infinity. Well-known asymptotics written here. So here we have a cosine, here we have a sine, and let us make up a fake exponential of these two functions. Namely, if we consider this function written here for w positive and is complex conjugate for w negative, then we have this asymptotics. E of w is the exponential of I w modulo a lower order term. So I call this a fake exponential. Well, okay. What further? Consider our Lagrangian manifold with a fold. And here is the canonical operator on singular chart. Well, let us single out symmetric and antisymmetric part of our phase functions. T of x is the symmetric part, and phi of x is the antisymmetric part. The idea is to replace the exponential of this antisymmetric part by the fake exponential. So if we do this formally, we obtain this expression written here. Well, somehow this E must be in front of the, so this is E of phi of x over mu, and this is E of minus phi of x over mu. So I have replaced the exponential by fake exponentials. It turns out, after careful analysis, that this expression already has no singularity at all. All the singularities that can occur, they cancel out. And this, if we then substitute the expression for the fake exponentials by the area function, we obtain the representation of k lambda phi via the area function of a composite argument. Well, okay. So, here we have an example of a Bessel's function of arbitrary index. We start from the Shafrir formula written here. The integral is over this contour. And we will study the asymptotics of j nu of z as this square root of z square plus nu square tends to infinity. We can actually discard the integrals over the upper and lower part of the contour, and only this remains. And here we have an introduced cutoff function, so that remainder will be small. This is an oscillatory integral with small parameter, and so can be represented by the canonical operator. Here are the Lagrangian manifolds, L gamma corresponding to this phase function written here. Well, and here it is the asymptotics of the Bessel function via this canonical operator. Well, okay, so here it's written by the area function. And here is some numerical comparison. I carry out computations for nu equal to 1. It is on the left, and nu equal to 8 on the right. So the solid line is j nu of nu x, and the dotted line is the approximation provided by the canonical operator. You can ask where the dotted line is, but they almost coincide, so that we cannot see the difference. So to see the difference, here it is. This is the error magnified by a factor of 100. So the solid lines are the exact values of j nu of nu x for nu equal to 1 or 8, and the dotted lines are the approximation errors multiplied by 100. So even this is a very strange phenomenon. known as the theory of canonical operators, that often, even if the canonical operator gives asymptotics and the small parameter tends to 0 or the large parameter tends to infinity, the asymptotic is very good already for very small values of the parameter. Here, the asymptotics is in the number nu tending to infinity, but however, the answer is very good already for nu equal to 1. So this is, well, the fact. So a similar construction can be carried out in a neighborhood of a standard cusp point. Here it is shown, but I am afraid I have only 5 minutes, so I cannot discuss this in any reasonable way.
Yes, you have 9 minutes.
10 minutes?
10 minutes, yes.
9 there. Okay, then I
minute
discuss this half reasonably. Okay, well, so the next singularity in the Arnold-Warchenko-Gusein list is the standard cusp A3. Here it is shown the cusp point on Lagrangian manifold, and if we speak of the standard cusp, then this is how the projection looks like on the x-plane, x1, x2. Here is the blue line is the caustic. Here we have between the caustics we have 3 real roots. On the caustic we have 2 real roots. That is 2 branches of Lagrangian manifold, and here we have only 1 real root. And so the problem is again to represent this integral canonical operator on this cusp, which is given by this formula via a special function. If the amplitude A here in this integral is equal to unity, then we obtain the special function known as the Pearcey function. Namely, we have this formula where the Pearcey function is given by this integral. For the general amplitude, we have the following. The first equation of the manifold has this form, and hence we can represent the amplitude in the form of this polynomial of P1, quadratic polynomial in fact, plus this remainder. This is just by Malgrange preparation theorem. And if we substitute this expression into the formula for the canonical operator, then we obtain the following. This term gives a remainder estimate because we can integrate by parts. And these terms give the following. Here we have rho naught times the Pearcey function. Here we have rho 1 times the z derivative of the Pearcey function. And here we have rho 2 times the second z derivative of the Pearcey function, which in fact equals the first y derivative of the same Pearcey function. Of course, the problem is we don't know the coefficients rho naught, rho 1, and rho 2 yet, and we should compute them. But we have the corresponding procedure in the domain where there are 3 real roots. These polynomials are obtained as coefficients of the interpolation polynomial by these formulas. And outside this domain, we use some continuation procedure, which I'm afraid I cannot explain now. But this procedure is efficient. Let me only say that what happens here, let me return to this drawing. We have determined the coefficients rho naught, rho 1, and rho 2 here between the whiskers of the caustic. And we need to find them here. Of course, we could somehow continue them across this line, across the caustic, but the problem would be here, at the cusp itself, because here the continuation through this line is not well defined. The recipe is to lift our considerations to the Lagrangian manifold, where this line, the caustic, becomes a line of focal points, and it is smooth, and then we obtain the answer. Okay, for a generic A3 cusp, again, we use a change of variables to reduce it to the standard cusp, and these changes of variables are computed again by some equations on the Lagrangian manifold. So at this point, could you possibly list down through the last page, very last page? Well, no, I will just say that there is written thank you on that page. So, well, maybe, okay. So that's basically all. I am finished.
Okay, let's thank our speaker. Are there questions, comments?
Do I understand correctly that your Lagrangian manifold is always a smooth submanifold of the phase space? That all these caustics, cusps, and so on result from projection to the configuration space?
Yes, a Lagrangian manifold is a smooth submanifold of the phase space. The caustic arise as the projections of the lines where the differentials of the projection is not of full rank. And in some cases, the focal points, the points of the Lagrangian manifold, form a smooth manifold, and the projection of the caustic has cusps, for example. In more complicated cases, the set of focal points in itself may have singularities, of course. Then we need further resolution of singularities. But I not to discuss.
Your construction deals with a four-dimensional phase space and two-dimensional configuration space, isn't it? Or you may work in higher dimension.
No. We work in the phase space, but so sometimes I can go into details. You need to uniformize your equation. That is, introduce additional variables, and then you get so-called resolution of singularities. This is a very long topic. I can't answer this in a short answer. So,
thank you.
Are there any other questions, comments? If not, let's thank again our speaker. And we will resume at 12 in 21 minutes.
Professor Bock, are you here? Hi. Could you please switch on your microphone?
Hello, can you hear me? Can you hear me?
Hello, now we can hear you very well. Hi. Yeah, and we see you now.
Okay. Let me just check.
Still, we don't see your presentation.
Just a second. I thought I would share my screen.
Yes.
Do you see my screen? Do you see my presentation?
No.
Let me check. Ah, okay. Can you see my presentation now? No.
Not yet.
Wait a second. I've tried to share it, but apparently this did not work. Now?
No. No.
What is the problem? No, neither, right?
Oh, maybe now.
Can you see it?
No.
Because when I look here at the options, I have 4 pictures that would show the presentation, but it should be this one. Can you see it?
No. So you are trying to share your screen and you don't succeed.
So I'm really sharing screen number 2 here. Let me see, what else can I do? You see this one?
No, nothing changes.
Nothing changes. I don't understand. I'm working here with 2 screens. And maybe I just reverse the 2. Hmm. Strange, because it did work. It did work on Tuesday.
Yes, yes, it did work. So maybe you quit Teams now and enter again.
I don't.
Professor Bock, can you send us your presentation and we can just switch slides if you want.
Yeah, okay. That I can do.
Connect.
Give me your email address.
Okay, send it on our email, please. Are you sent your file?
Hello?
Yes, we're here.
But you still don't see my screen, right?
Right, yeah. We can see nothing.
Because I'm sharing the screen. I can also share the presentation, but nothing helps, right? You don't see anything.
Yes. We have two options. You can try to reconnect into Teams or send to us your file with presentation. We're going to demonstrate the screen and you just going to say to next slide and we're going to switch
Yeah,
slides.
okay. No, it's okay. But you have to, where to send it to?
We wrote for you emails from our email post. The FDE.
Okay. You just send me an email? Okay. Wait.
Or you can send it into chat, Teams chat. Try it, it's better to send using email.
Okay, just a second.
We were waiting for you.
So I have mail here from Alexander Skubachevsky, Professor DFDE 2020 at mi/-ras.ru. That's where I send it to?
2022.
Okay, yes. DFDE 2022
yes.
at Math Institute minus Royal Academy of Science, I guess, .ru.
Yes, right you are. We are waiting for you.
Okay, well, I'll send it to you. Wait a second. Sorry that it doesn't work today.
It's okay.
So it's uploaded, 5 megabytes. And I just sent it.
Are you sent it your email?
You got the email?
We don't get it. Email. Are you sent it?
I've
Yes?
sent it.
Strange. We can't see it now. You just replied on previous letter using right address, or you just reprinted it?
No, I just sent the PowerPoint file.
Yes, on our email address using reply function, or
yeah, I was using the reply function to the email where I was sent the links for today.
Okay.
So I just read again which email which address I did send it to. DFDE 2022 at mi-ras.ru.
Yes, this is the right address.
So, but it's 5 megabytes because there are 3 videos in it. I have just sent it again, just to make sure.
Maybe you can try again to share your screen because we don't see any email on our post.
Which is
You can-
strange. I've sent the email twice.
Yes, that's strange. Right, you are. But can you try to reconnect into Teams using our link again?
Yeah, I will start. Okay, I will start everything from fresh. Wait a second.
Hans, are you here? Professor Bock. You can switch on your microphone. We got your presentation. Now we're gonna share our screen. You can begin your report.
Okay, now you do you have, did you get the email or?
Yes. So we get it.
Oh, you
can
have the
see
email.
presentation?
Okay.
Okay, with the great delay, we start the lecture of Professor Bock. The title is on the screen, but we have to shrink the duration slightly. Please appreciate the situation and try to be more brief than it was expected. Please, Professor Bock.
Hello, I'm here. First of all, I apologize because the major problem was I was mistaking the starting time actually because of the time difference in time here. So what I'm talking about is inverse control problems as a new way of modeling the gait of people, in particular of people suffering from cerebral palsy. And so based on a long-going cooperation with the Interdisciplinary Center of Scientific Computing, my institute, and the Motion Lab of Heidelberg University. So next slide, please. Next slide, please. So the motivation is modeling the gait of cerebral palsy patients. And as a model, we choose state and control constrained optimal control problems, which should serve as a model for any kind of control dynamic processes. We'll talk about three aspects of the inverse optimal control problem: the parameter estimation problem to identify the model, then the direct and all-at-once multiple shooting approach to solve the problem, and then the difficulty that is appearing because we have complementarity constraints, a lifting approach. And finally, I give you an application versus showing you healthy versus cerebral palsy gait of people. Next slide, please. So the motivation, next slide, is cerebral palsy, which is a serious handicap and heavy burden for more than 700,000 people in Europe. And these are in particular pathological disorders which are caused by disturbances in the development of the brain. For instance, during pregnancy or during birth. And it happens in about 1 out of 500 live births that we have in Europe. So it's a pretty high number. And this deficiency of the brain then affects the muscle development and coordination. And from there, it goes on to that the spastic muscles that you have lead also to deformations on the skeleton and on the joints. And you should see a video in the upper right corner. Maybe you do have to start it. Normally, in my case, it would start automatically. You don't see the video here in the upper right corner. Yes, please. Please click there. So it doesn't seem to start. Sorry. Too bad. So what happens is what you should have seen there would be the gait of a handicapped person. That is what orthopedians call crouched or assisted gait. Unfortunately, for such a defect, no cure exists. There are only orthopedic interventions, which usually mean surgery to mend the problem, to hope to mend the problem. Next slide, please. So what we want to develop is a model for a patient's gait and we want to validate it by measurements from the motion lab. So, of course, there are, one item is that we would like to understand human motion in general this way, but in particular for the collaboration, we want to develop a quantitatively and qualitatively correct and validated digital twin of such an individual CP patient and his way of walking. In order to allow for identification of the dynamic and kinematic parameters in the model, such as force and torque histories and physiological pathologies from the marker measurements. And the ultimate aim then is that we want to use this as to develop mathematical tools to support the physician in the clinical practice, such as develop tools for precise diagnosis and classification schemes, but also ultimately also for support of treatment planning and therapy assessment based on the predictive particular properties of the patient. Next slide, please. So what we need for diagnosis is something like a mathematical look inside. We have measurements from markers that you can see on these three pictures, markers on the body, and we can measure them with the video equipment. And from there, we want to determine the pathology, so irregularities of the bones, of the joints, of the muscles, of the tendons, and so on. And also to determine some dynamic parameters like the joint forces happening in the joints, or rather torques, because they are rotary. So, but the only data that we have are non-invasive measurements, like measurements of the time history of these markers on the body. And a few more kinematic markers of the patient gait. So next slide, please. How do we model this? The model should be an optimal control problem. Next slide, please. So far we don't have any reasonable dynamic model for a human's gait that would suit our purposes. And so we follow what Leonhard Euler called the nature's optimality principle, that nothing in the world will occur without a maximum or minimum rule somehow shining forth. So our modeling assumption is we assume that the human gait pattern follows certain optimal or optimality or optimal control criteria under restrictions. And there are similar applications from modeling the dynamics of a human-driven vehicle to modeling in differential games to modeling the partner strategy, for instance. So next slide, please. So what we want to have is a model to determine controls and states satisfying an optimal control problem. I've written here an ordinary differential equations. Next slide, please. But indeed, as you would see at the end of the presentation, we have a much more complex mechanical multi-body systems of equation, a differential algebraic equation of index 3 with even changing degrees of freedom and discontinuities whenever we have impact. Because it is a very different model, whether you have 2 feet on the ground, left feet on the ground, or right feet on the ground. Next slide, please. So we have, in addition to such a dynamic model, we have boundary constraints, inequality constraints on the body, knee stroke, ground contact, torque and angle constraints in the joints. And we would like to minimize, we assume that we minimize a cost function, or rather a sum of different criteria of cost functions. And now arises the model validation problem. Does this model, and what kind of model and parameters reproduce the experimental data? Next slide. So we end up with the inverse optimal control problem. Next slide. So given the experimental data from the gait lab, determine the model and its parameters, gamma for the cost function and p for the system's dynamics and constraints that reproduce the data best. And let's skip this slide because the comment, I had the cartoon here of a classroom example of the peanuts. Okay, well, skip this because we only have 20 minutes left, I suppose. Next slide, please. So we have experimental data which are not we are not measuring the state variables of our model, but rather complex function of the position of the markers, and that needs considerable extra modeling. And the data that we have come from multiple experiments, usually from the motion lab. Next slide, please. So we have a parameter estimation problem, and assuming for simplicity that it's normally distributed errors, then we want to minimize some the deviation from the least squares function, deviation from the measurements, where the state variable x and the controls u are a solution of an optimal control problem with unknown parameters gamma k. There in the cost function, and p describing constraints and the dynamic model. So there's a very complex set of restrictions that we have to satisfy. Next slide, please. So we have two optimization problems. The lower level is an optimal control problem, and we replace it by a necessary set of optimality conditions. So we could use the indirect approach, the so-called by Pontryagin's maximum principle that I've sketched here, which would contain also possible jumps of the adjoint variables in the dynamics. And the optimal control problem is determined by the maximum principle, and we have these additional dual variables, or lambda and again mu and beta for the constraints that we have. So it's a non-smooth solution that we get here that enters our measurement functions. Next slide, please. So therefore, this is for one thing, it's possibly ill-conditioned because of the dichotomy problems that we can expect from the dynamic system there. We have state-dependent discontinuities, jumps of adjoints. We also can expect discontinuities in the controls. So we have a difficult solution, this structure, and unfortunately, this also depends non-differentiably on the unknown parameters p and gamma that we still have to identify. Next slide, please. So the alternative we choose here is the direct approach. And I start to be briefly, direct means we're iterating directly on the primal variables, controls, and states, and not on the adjoints as in the indirect or maximum principle approach. So we discretize the controls on a suitable time grid. We discretize also the states, in this case with our own multiple shooting method that we have developed decades ago. So we have discretized then state and control constraints also. And so we have only primal variables that enter now a nonlinear programming problem. Discretization of states, the S variables, and W, the discretization of the controls. Next slide, please. So we have the lower level replaced by the necessary conditions, so the multiple shooting conditions up there from the discretization of the primal problem, and then the Karhush-Kuntaka conditions from the optimality principle. And I've underlined in blue that we have a complementarity constraints there. We get, again, discrete, of course, dual variables, but they serve only as complementary variables. Next slide, please. So for the treatment of the upper level, there are two possible ways. The one is feasible point approach. We would always solve the optimal control problem on the lower level, and then solve with any kind of suitable optimization methods for non-smooth problems on the upper level, say by a Gauss-Newton method for the least squares problem. But we have chosen and developed a different so-called simultaneous or all-at-once approach. We solve both the discretized lower level optimal control as a constraint and the optimization of the upper level in one loop by a special generalized constraint Gauss-Newton method. And that was major work also from the doctoral thesis of Katrin Hartz, is one of my co-authors here. Next slide, please. So we end up with a large but structured constraint least squares problem, minimizing the deviations there. And then in the discrete form, we do have complementarity constraints, of course, because we have inequality constraints, and we do also have this complementarity constraints that you see by the green arrows there. So we have to solve that with a special tailored method. Just a next slide, just an example. Next slide, please. So this, what you see here, is the special structure just of the constraint Jacobian, because that's the KKT matrix that corresponds to the lower level optimization, which has the necessary condition for the lower level optimization problem. So it's a relatively complex problems because we also have to come up with higher order derivatives now for the differential algebraic solution equation, and the size roughly triples. Okay, next slide, please. So there are several numerical challenges here because it's, well, maybe I just skip this and continue. Next slide, please. So one particular problem is that because of the complementarity constraint that we have, the optimization problem on the left side, where we have an optimization, lower level optimization problem and an upper level optimization problem, so a bi-level problem, the lower level contains a complementarity constraints because we have this Z transpose A must be greater or equal 0, but Z in H also greater or equal 0. And one of the problem is that such problem, now we have an optimization problem that lacks the, that we don't have the linear inequality constraint qualification at any feasible point. So we get infeasible QPs arbitrarily close to the solution. And as a remedy for this, next slide, we have in a paper together with Sven Leifer from Argonne, developed a select method, a lifting approach by introducing an additional variable W and penalizing it at the same time. Next slide, please. Next slide, please. So as you can see, the green line there in such a classical performance profile, the green line gives a much better performance. It's much faster and solves many more problems correctly. From a test set of 146 problems. Next slide, please. So now I come to the conclusion already and the real application. So we have a simplified 3D mechanical multi-body system model. You see the illustration on the left side. We really have such a mannequin that should resemble the body, the body of a person, and then also it's walking. So it has 20, in a mechanical sense, it has 24 degrees of freedom and 48 states, not too big really, the system of differential algebraic equations. We have 3 global coordinates, 3 global angles, and 18 local joint angles, which are driving the problem. And then of course the corresponding velocities as well. So we have 18 controls, lots of unknown parameters about the joints, the length, the weight or the inertia of the different bodies and so on. And so we need to have a truly, in order to actually resemble a real patient, we have to have a truly 3D gait, a 3D hip, 3D knee, 3D ankle joints. And the model, to formulate the model, we would use a toolbox that was developed by Pierre Weber, one of our collaborators. So the data that we have, I mentioned before, are motion capture data of these markers and just a few ground force data because there are sensors under the on the walkway. So next slide, please. So this is the dynamic system, and just to illustrate the changing degrees of freedom. So we do really have a differential algebraic equation, and the algebraic equation there is nonlinear and is of order 3. So we have to do index reduction in order to actually be able to solve it. The next slide shows that we also have changes phase-wise. So first we have one foot on the ground, then the second foot is on the ground, then one foot is lifted again, and each time we have different variables and degrees of freedom, so the model changes. And whenever we hit the ground or leave the ground, then we do have, when we hit the ground, we also have impact, that is changes in the impulses. Okay, next slide, please. So now the final problem is we want to compare healthy versus cerebral palsy patients and see what their cost functions might be. So we assume that the cost function is a linear combination of 4 criteria we got from the physiology papers. So one would be maximum stability, which is kind of the squared distance between the supporting foot and the corresponding hip joint. Then minimize energy in terms of the input torques that we have in the joints, and 2 comfort functions which are the rotation of the z-axis in the hip joint and the abduction in the hip joint. And we would like to identify the relative distribution of these optimization criteria. Next slide, please. So here we see the result for the cerebral palsy gait. And unfortunately, this video should be running because it shows both the identified gait and the measured gait. Can you get the video running? Please try to start the video. Unfortunate. Since unfortunately we did not get the presentation running, so what we do have, the result is, the numerical result is quite expectedly the patient, which has very distorted joints and ankles and bones, mostly concentrates on the stability, so not to fall over. And only a very small percentage goes into minimizing the effort going into the joint forces. And what you unfortunately cannot see from the gait, that the model in green, the data in green and the digital model agree by roughly like 3 to 5%. So it's a pretty good agreement for a relatively simple model. Next slide, please. And here is the reference gait of a healthy person. And for the healthy person, doesn't care at all about the stability. The effort goes mostly into being economic with the amount of energy going into the joint forces, and 2 criteria that improve the comfort, so not to rotate the hips too much and so on. And again, the agreement here is about 3 to 5%. So that kind of ends already almost my presentation. Next slide, please. So this is then the summary. So we have Dirac, we have developed a new method, in particular structure exploiting generalized Gauss-Newton method that can deal with Gauss-Kuntaka conditions of a complex problem as they're constrained. For the appearance of the complementarity constraints and the lack of the linear inequality constraint qualification, we have developed a novel lifting approach in order to overcome this problem. And so we have arrived at a novel model for human gait that we can now use in our collaboration with the orthopedic lab to develop tools for the physician in the lab. So work in progress is, on the one hand, to extend the models, more complex feet for the ground contact, more complex muscles and tendons in order to model the specific dysfunctions of CP patients. classification schemes that the medicine people actually love, and then to develop tools for the diagnosis, but also for the treatment planning, including rehabilitation and therapy quality assessment. So next slide, please. Thank you very much for your attention in this talk, and I'm also very sorry about the problem we had, the technical problem that we have had to deal with. Thank you very much.
Thank you very much, Professor. You successfully overcome all the technical obstacles, and anyway, I am afraid we have maybe just a little time for very brief one question, if any. Yes, sure. Please.
Excuse me, could this model be extended to treat patients who suffer from amyotrophic lateral sclerosis or some other degenerative diseases of central nervous system? Those are rare diseases which also affect motion, and as such they are not very well studied.
Yeah, yeah. Well, the model that we have developed can of course be extended and could involve also by extensions of the model all kinds of problems that could be treated in orthopedics. Of course, it does not contain any physiology so far, and it would be difficult, of course, any physiology, any cell structures or so. It is really based mostly on the muscle, tendon, skeleton system and deficiencies there. If we would like to go more deeply into actually what happens in the muscle, like certain defunctions in muscle weakness, for instance, then that would require different models. But this is a model for the movement, for the gait of the body.
Thank you again.
Thank you very much.
And now we have no break at all. It's time for the lecture of Professor Shafrir. Professor Shafrir, thank you for your waiting. And now it's your time. You have all your 45 minutes, please. Do we have the presentation of Professor Shafrir? Ah, yes. No, not yet. Yes, we see a presentation. Please start.
Can you hear me?
Yes, we can.
Okay.
We hear you and we see your presentation in the full screen mode.
Thank you. So everything is working all right. So I would like first thank the organizers for this really great honor to give a lecture here. Thank you again. This is a joint work with Dmitry Golovaty from the University of Akron, and actually is originally from Moscow. The motivation comes from a model, the Ericsson model in liquid crystals, but most of the lecture will be about the analysis, as you will see. So the simplified Ericsson model is a model in which the energy of a liquid crystal is given by the following formula. So So K is a parameter, but the variables are S and N. S is a scalar, non-negative scalar, and N is a function on the three-dimensional domain omega, taking value in the sphere S2. In my lecture, we will reduce dimension eventually, but this is the original physical problem. And there is also some simplification. For example, there is a potential term that we omit here, but it is omitted also in other works. There were quite a few studies of this energy in different settings by these authors below. Questions of existence of minimizers, regularity, numerics in the work of Nochetto et al., and so forth. Now, there is another way, equivalent way to represent the energy using a single unknown, U, by writing U equals S times N. So now, since N is in S2 and S is a scalar, U takes its value in R3, and S is the modulus of U, and N is the direction, U over the norm of U, as you can see. And then the energy, the pointwise energy, the density of the Dirichlet energy of U is this, given by this expression. And so using only U and the modulus of U, we get this representation here. The reason why from K here we pass to K minus 1 is that in the gradient U square, you see there is also one, the gradient of S square appears once. So this is the reason why for this equality. And we will study, between quotes, the non-physical two-dimensional case. So I mean that U is defined on a two-dimensional domain in R2, and also the target is R2 and not R3 as in the original physical problem. The truth is that we have some setting of a scene field model where we can show that the two-dimensional model is also relevant, but I don't give details here. So we work in 2 dimensions. So again, this is our problem, but we have this energy as before, but we minimize over maps with the boundary conditions. So you see this little g here. So you should satisfy the boundary condition g on the boundary of omega, where g is a smooth given function from the boundary of omega to S1. And since people usually are using small parameter epsilon, so we are interested what happens when k goes to infinity. Instead, we introduce epsilon as 1 over square root of k, and we are interested in what happens when epsilon goes to 0. So our energy from now on will be this expression. We have a term with u, a term with the energy of modulus of u, but with this coefficient that becomes big when epsilon becomes small. And the boundary condition should be satisfied on the boundary. And the problem is what happens when epsilon goes to 0, which is equivalent in the original setting here when k goes to infinity. Just one small remark, you see that you just have Dirichlet energy of u and modulus of u here, so the energy is conformally invariant, and we can, when it is convenient, we can pass from any simply connected domain omega to the unit disk B1 using this conformal invariance. Now, this type of problems might remind you a famous problem, which is the Ginzburg-Lano energy, where again we have omega in R2, bounded, smooth, simply connected, and the boundary condition which takes value in S1, but the energy takes this form. So you see, you have also penalization with epsilon small, but it's on a term of this type, not a potential term, not the gradient of the modulus square as in our model. Again, with the boundary condition G. And the idea, which is similar actually to what happens in our case, when epsilon goes to 0, you expect the minimizer to be closer and closer to be S1 value, because whenever the modulus is not 1, you penalize. So in the limit, you expect to find a map which takes values in S1. And it should also satisfy the boundary condition G. And the famous work by Betuel and Delan. So you have two parts. If the degree of G is 0, you can write G as EI phi 0 for some scalar function, the phase of G on the boundary. And then, this is because the degree is 0. And then you can look at the harmonic extension of phi 0, which has the smallest possible energy for this boundary condition. And so this U0, which is EI phi 0, is the natural candidate for the limit. And indeed, this is what they showed, that U epsilon converges to this specific U0 as epsilon goes to 0, and the convergence is in C1 alpha, up to the boundary. On the other hand, when the degree is not 0, assume it is positive, greater or equal to 1, then you cannot write anymore, you don't have a lifting for G. For example, take on the units disk, on the boundary of it, take EI theta, just the identity. You cannot use the lifting theta, you cannot extend it, it's not even continuous on the boundary. So you have a problem when the degree is different than 0. And then you know that there is no a smooth extension in the interior, which is S1 valued. And so, unfortunately, you must have singularities. And the result is that indeed, up to subsequence, the minimizers converge to a map U star, which is indeed S1 valued, but it has singularities. And you have exactly these singularities of degree 1, where D is the degree. And the convergence, otherwise it's C1 alpha away from the singularities. And the expression for the energy, so it blows up as epsilons go to 0, but you know exactly how it blows up. It blows up as 2 pi d absolute value of log epsilon. And the remainder term, the O1 term is completely known. Gamma is some universal constant. D is the degree, and WAG, this is an important term that actually depends on the points of the singularities. So the chosen configuration A1 to AD minimizes some specific function of D points in omega. This is the function WBG. And for A equals B, you get the minimum, and this will be the location of the singularities of the limit U star. Okay, that's all. Now back to our energy, where the penalization is on the gradient term. Okay, so just as a warm-up, let us consider a specific case where we are working in a disk around 0 of radius r, and the specific boundary condition is this one, G r EI theta equals EI d theta. So it has some specific symmetry, and you can consider functions that satisfy this boundary condition, but of this specific ansatz. So FREI d theta. We don't know a priori that the minimizer should have this form, but we know that such map exists, and we can minimize in this class of this symmetric functions. So in this case, we have only to minimize over the modulus f of r. which is, so it becomes a scalar ODE problem in some sense. And the claim is that in minimizing over this class, the solution is very simple, and the energy of the minimizer is 2 pi d over epsilon. And in a moment, we will find actually what is the form of the minimizer. So I didn't write explicitly what is the admissible class V, but this is exactly what you can imagine. It's a class of function for which this energy is bounded. And just writing first the energy of the density of the energy of a sum of 2 squares, as we did here, and using Cauchy-Schwarz inequality, we get this inequality is that the lower bound is 2 pi d over epsilon, but it turns out, that we can identify what the point was the cases of equality in the Ginzburg law in this Cauchy-Schwarz inequality, and finds that what is the only possibility for a minimizer, and this minimizer is actually R to the power of d epsilon normalized in order to have f equals to 1 on the boundary. So okay, so this is just, it's not a solution for this boundary condition in the general case, but under this ansatz, this is the solution to this minimization problem. But it turns out that it gives us some insight to what happens in the general case. And it turns out that we can use quite similar ideas for finding general lower bound for the energy in the general case. So the claim is that this lower bound that we found before is valid for any boundary condition of degree D, not necessarily the symmetric one. So let me, maybe you see in the picture here actually what we do. We use the co-area formula, and we the first line, we just wrote what is the energy. And then we use Cauchy-Schwarz, just a point-one simple Cauchy-Schwarz. And then we decompose the total energy according to the level sets of the lines modulus U equals T for each T between 0 and 1. And then you see you have the gradient of the phase of U. This is actually something that you can bound from below by for each fixed T, you can bound from below by D, by the degree. And then we just get a very simple lower bound, the integral of T between 0 and 1, multiplied by this constant, and we get again 2 pi d over epsilon. So you see in the picture that for small values of T, you might have, here it's a case where you have 2 zeros of your map U. So you have two lines, or let's say that the level set composed of 2 components, two closed arcs, but when you increase T, you get just one component. But this is independent of the number of components, the lower bounds that I find for each fixed T. And so if we want to complete what estimate we have about the behavior of the energy of U epsilon, we actually have a complete solution here. We just proved the lower bound, 2 pi d over epsilon. And in order to prove an upper bound, which is written here, 2 pi d over epsilon plus C, we can use actually the case of disymmetric boundary conditions that we considered before. We can assume that we have a disk of radius r contained in omega. In this disk, we plug the function v epsilon that we found before. And we just have to complete in this type of annular domain between omega and the disk by some S1 valued maps that on the circle of radius r equals EID theta, and it equals to D on the outer boundary. Okay, so actually, before what I write now, it's quite surprisingly that we have, as far as the energy is concerned, I gave you almost a complete proof of this estimate. So we know what is the behavior up to an O1 term, while in the Ginsburg-Landau energy, one has to work quite hard in order to get the lower bound at least. The upper bound is quite easy also there, but we are lucky to have a complete estimate quite easily. But we shouldn't be too happy because we still have a work to identify the limit, to prove convergence and identify the limit. Yeah, so we haven't done yet. Now we saw that the D-symmetric case is special, where we have some special insight. It turns out that it's just a special case of a more general class of boundary condition associated with Blaschke products. Since we have this conformal invariance, it's not so surprisingly that we see some connection to the theory of conformal maps in the plane. So let us assume that omega is the unit disk and consider D points, A, J going from 1 to D, and associated Blaschke products. We don't assume that the points are necessarily distinct. So if all the Aij are equal to 0, to the origin, then we get D-symmetric functions that we considered before, as Z to the power D. And it turns out that here, again, like in the D-symmetric case, we actually can identify the minimizer exactly. We have an exact form for it. We just keep the phase of the Blaschke products, taking f of z over modulus of f of z, and multiply it not by the modulus of fz, but the modulus to the power epsilon. And it turns out that this is actually the minimizer, and the energy equals exactly to 2 pi d over epsilon, which is the minimal possible energy as we saw before. Maybe I skip some details. I skip here because it's really related to the fact that we work with conformal maps and there is some connection. The phase is the harmonic conjugates of the log of the modulus, and we can use this. For u epsilon, we don't take the modulus as it is, but we take the modulus to the power epsilon, and we have some equalities here related to this. The fact that the phase and the log of the modulus are harmonic conjugate of each other, and there's a special relations between them that gives us exactly what we need to have equality in the Cauchy-Schwarz inequality that we use in the proof of the lower bound there. We're using the core formula. As I write here, yes, this implies equality in the pointwise Cauchy-Schwarz inequality used before. And as a corollary, we can go back to the D-symmetric case and conclude that this is just a special case. And what we found here, minimizing over the class of D-symmetric case, is actually the true minimizer for considering all admissible functions without assuming any symmetry. This special form of U epsilon is really the minimizer. Now I'm taking a break from the general case and go to the special case of degree 0. The case of degree 0, as we saw also in the Ginsburg-Landau energy, is simpler and different because there we have a lifting for the boundary condition. So we can write G as EI phi 0, and we have a natural candidate for the limit, an S1 valued without singularities. This is the map U0 equals to EI phi 0 tilde, where phi 0 tilde is the harmonic extension of phi 0. And then we have indeed convergence of U epsilon to U0. And we have also an estimate of the error. The error is of the order epsilon square. It's a little bit different from what happens in the Ginsburg-Landau case. So just the idea of the proof, convergence in each one is easy, and the main point is to show that the modulus rho epsilon, the modulus of your epsilon goes to 1. Once this is achieved, we can write the Euler-Lagrange equations for u epsilon separately for the phase. This is the left equation, and for the modulus, this is the right equation. The Laplacian of rho epsilon equals what you see here. And okay, no details needed here. Let's go back to the more interesting case when the boundary condition is of degree d greater or equals to 1. In order to analyze the minimizer in this case, we use the method of bed disk. It's motivated by what was done in the Ginsburg-Landau case by Bethuel, Brezist, and Elan, but here the technique is used a little bit different. So the idea in general is, look, what is the bed set? The bed set essentially should contain the zeros of u epsilon, because eventually this leads to the singularities of the limit. So we look more generally on the set where the modulus of u epsilon is smaller than some beta, where beta is smaller than 1. So it turns out that S epsilon can be covered by a finite number of bed disks. This is what is also proved in the Ginsburg-Landau theory, but here it is convenient to use actually a hyperbolic bed disk of radius, you see, of the order exponent of minus c over epsilon. So they are much smaller than the bed disk in the Ginsburg-Landau case, which are of the order epsilon. And then we can cover S epsilon by a finite number of this type of bed disk. And this is possible using the following properties that should require a proof, of course, that if at a point A, the modulus is smaller than B, so A belongs to this bed set S epsilon, then the energy of this of an hyperbolic disk of this radius center at A is bounded below by something of the order C over epsilon. Since we have also a global upper bound of the order C over epsilon, this leads to a finite cover of the bed set by a finite number of bed disks. Once you have this information that you have only a finite number of bed disks, it helps, and you can move to the convergence of u epsilon. So thanks to this property, we know that the modulus of u epsilon is close to 1 in most of the domain, but besides a finite number of bed disks. So about the modulus, we have quite good information already. But now the problem is to control the phase. So you see in the pictures that the bed disks are given in green here, and ignore zeta, equality, etc. This is technical property quantities that we use, but you have to control the phase outside the bed disk, and this is not trivial, but we managed to do it using a method that appeared in a paper of Petro Mironescu of myself that dealt with another problem, but we can use the same technique here, adaptation of it, in order to control the phase as well, not just the modulus. There is an idea there finding good lines, which might be actually circles, because we're working in with hyperbolic geometry, connect to the boundary and work in the domains that left. And using this, we can prove our first convergence result. So the assumptions are as before. First, I just recalled what we know from the energy. We knew it already before. But now for the convergence, we have indeed convergence away from a finite number of points, A1 to AN. And the limit U star is again, it has it has singularities at the point AJ, J going from 1 to N. But otherwise it has somehow the simplest possible structure you can expect from a singular map. It must have singularities, but at least it has this simple form. The difference with respect to the Ginzburg-Landau case is that we might have singularities of degree dj strictly greater than 1. Actually, we saw that in the d-symmetric case, we have just one singularity at the origin of degree d, where capital D might be 2, 3, 4, whatever. So we might have degrees greater than 1, strictly greater than 1. This is what I remarked here. This is very different from the case of the Ginzburg-Landau energy. But of course, the question remains how to identify U star. And this is the content of the second theorem. So let omega, for simplicity, we can always assume that omega is the unit disk. G is the boundary condition of degree capital D, and U star is the limit. Sorry. There was a question? No. Okay, so AJ, J going from 1 to n, are the singularities of U star, of the limit, and DJ is the degree around the singularity AJ, as in theorem 1. Let me show you again the picture. So you see U star Z is EI phi, where phi is just a smooth harmonic function that is chosen by the fact that the boundary condition of U star must be equal to the boundary condition little g. And AJ are the singularities. So I'm going back to the theorem 2. Then we have the following. So the energy behaves, as we know before, the energy behaves like 2 pi d over epsilon, but now we can completely characterize the remainder term, the O of 1 term. Yes, the singularity is like 2 pi d over epsilon. When you subtract it, you get some expression. Now this expression, this quantity, I denote it by d h1 square. So it's, okay, so let me say in words what it represents. You take your boundary condition G, which is a map from S1 to S1, and you consider the distance, in some sense, of this G from all the Blaschke products consisting of D points, with D zeros. So it's B1 to BD, which are not prescribed, but are D points in the unit disk. Okay, you see below, BD of omega is the set of all Blaschke products of D points. And I look, what is the distance of my boundary condition from this set of Blaschke products. So you see, if G is itself a Blaschke product, this is the case we considered before at the beginning, the distance is of course 0. And that is why we get for the energy exactly in the limit 2 pi d over epsilon. Otherwise, it should be some positive quantity. Now, let me just explain, of course, what do I mean by dh1 here? Okay, so, okay, just to complete the, I will say in a moment what is this distance, but assuming we know what is the distance, so the singularity is chosen by the limit U star, they realize the distance between G and the Blaschke product. So in some sense, you look at the projection of G on the set of Blaschke products, and the nearest point projection is a specific Blaschke product. You look what are the points in these Blaschke products, and these points A1 to AD are the singularities of the limit U star. So what is this dH1 half. Or dH1 half square. So you look at of all the possible Blaschke products with points B1 to BD. And once you fix this Blaschke product, you should look at the distance between G and this specific Blaschke product. So how are you defined? You have to define a distance between two maps from S1 to S1. One is G, the other one is the specific Blaschke product. So what do? First, you divide G by this Blaschke product. What you get? A map from S1 to S1. But this map now has degree 0, because we divide a map of degree D by a map of degree D. We are left with a map from S1 to S1 of degree 0. So for a map of degree 0, you can write it as EI phi. It has a lifting. Okay, you have the lifting phi, which is a map from S1 to R. Take the harmonic extension of it to the disk, call it phi tilde, and look at the Dirichlet energy integral of gradient phi tilde square. And look at this quantity. This quantity is what I denote by the H1 half distance between G to a specific Blaschke product. Now, minimize over all the Blaschke product. This is the DH1 half square distance between G and this Blaschke product, as I just said. This is the statement of theorem 2. This is actually give you the exact behavior of the energy and also the description of the limit U star. This gives you a precise description of the singularities of the map U star. Okay. Now, a few words about this excess energy. I call it this excess energy, dH1 half square between G and the Blaschke product. It has a specific, if you want, an explicit formula given here, where phi 0 tilde is a kind of a green function, it's something similar to a green function. It's a solution to a problem for harmonic functions, scalar harmonic functions, but with Dirac measures at the point Bj, and satisfying a Neumann boundary condition. And R0 that appears here in the expression is the regular part. When you subtract from phi 0x this sum of log x minus the logarithmic singularity around each point. Now, I didn't invent this this expression actually, or at least this function phi 0 tilde, because it appears in the renormalized energy that I mentioned at the beginning in connection with the Ginzburg-Landau energy. So this renormalized energy actually minimization of it determines the limits that they found in their model for their U star. When you compare the two expressions, they look very similar. You see the integral of phi 0 tilde G, this vector product with GT, G tau is the same. The term with R0 is also the same. The difference is in the last terms, that you see that in the dH1 half square term, you have log of the modulus of 1 minus BI Bj bar, while in the renormalized energy, you have something with the log of BI, the distance between BI and Bj. And you see it's an important difference, because in the renormalized energy term, you see this term prevents from Bi to be equal to Bj, because then you get log of 0 and you get plus infinity. So it's impossible. While in our dH1f squared term expression, nothing dramatic happens when bi equals to bj. Okay, you see, nothing blows up there. So, so this is the reason why in our case we can have limits with bi and bj can be equal. So we find limiting singularities of degree greater than 1, strictly greater than 1, which is not possible in the Ginzburg-Landau model. So you can see also from this point of view why you have this difference between the two models. Okay, I see that I finished even ahead of time. Probably I went too quickly. So in any case, thank you for your attention.
Thank you very much. Please, questions to Professor Shafrir.
Question about first part of the lecture. How the Ginzburg-Landau potential arises from the energy of a liquid crystal.
I didn't, mostly, in most cases, Ginzburg-Landau energy is used to model superconductivity and not, the model I consider as its motivation in liquid crystals, but Ginzburg-Landau energy actually is associated with the models in superconductivity. There are other versions of similar to Ginzburg-Landau that appear in liquid crystal theory, but this is not. I didn't say that. I didn't claim that Ginzburg-Landau is related, comes from liquid crystals. I mentioned it because it's similar to, in some sense, it's similar to the model I consider, but as we saw, there are also quite significant differences between the behavior of minimizers for these two energies.
Thank you. I see we have a question in Teams, please.
You restrict to the plane situation in the image. If you allow it to go in 3 dimensions, which may happen because it may go out the direction.
Yeah.
Then the singularities would appear because it would like to go out. But you have films, no?
Yeah. I didn't study the case. Also, the question what you asked, do you say from 3-dimensional domain to you want 2-dimensional?
2-dimensional, but 3-dimensional direction. It could move out.
Yeah.
Because the boundary conditions which you have are in 2 dimensions.
You could ask right. Yeah. There is this phenomena escape in the 3rd dimension, as they call it the physicists.
No. In fact, I have been looking at this for harmonic maps, and which are closely related to magnetic fields. And if you have forces, for instance, you can, the system would like to go out.
Yeah, I know. Yeah, so yeah, I didn't consider this. Of course, it's interesting, but you know, some of the main point from the mathematical analysis point of view for us, it's not necessarily physical, but mathematical is to have this singularities. In the case you describe, even without penalization, say you have a finite energy solution, and then it somehow.
Yes. Yeah, I understand, but they may disappear, the singularities, if you go
out. Sure, they will disappear. There will be no singularities. Yeah.
No.
Yeah.
But
the case, if I understand correctly, even without, as you say, harmonic maps, you have solution with finite energy. You don't have singularities in this setting. Yeah?
But you looked at what I would call films. Magnetic, liquid, they are films.
Yeah.
Because they are restricted to 2 dimensions. It's like magnetization, magnetic tapes. Because they don't.
Let me just verify that I understand correctly. Just take a simple case. You're working in the disk, but you go to R3, yeah?
Yes.
And suppose you give the EI theta boundary condition.
Give the same boundary condition which you have there.
With the boundary condition EI theta, the simplest one, yeah? And the harmonic maps going to okay, so if you go to R3 and you penalize, but even without penalization, if you just look at harmonic maps, taking values in S2, you have a solution without singularities, going to the upper.
No, it depends. No? It depends. No, you may also get. It depends on. It depends on the boundary what you give in 2 dimensions. You could have singularities. X over X absolute is one of them.
X over modulus X?
Yes.
But it has infinite energy. Yeah.
Yes.
But it goes to S1.
Wait a moment. Yes, but you could have allowing to go outside gives a chance to avoid singularities. That's. And but it depends also on the. You may get singularities depending on the index of the boundary, binding number on the boundary.
Yeah, sure. But you have to. But X over modulus X takes its value in S1, so somehow you force them to stay in the plane, as to say they might go away.
I give them the freedom to go out. They are only forced at the boundary to be 2-dimensional.
Exactly. So they will choose to go to the upper hemisphere and not stay in S1, no? If you give them the...
we can't... I think one has to discuss this.
Yeah, maybe I don't understand exactly what you say, sir, but we can discuss it later if you want.
Okay.
Okay. Do we have more questions? If no, then let us thank Professor Shafrir again.